Okay, now we asked the question, what's the work done per unit charge to move from a great distance to within proximity r of an infinite line charge with charge density lambda, lambda being in SI units coulombs per meter, number of coulombs you have per meter of length here. Now we have already derived the expression using Gauss's law. I'll mention that at the very end of this video, which will be fairly short. Okay, at position x star, the force is equal to the electric field multiplied by the charge. The electric field is this part of the expression, and the Q is this expression. Remember, the electric field is the force per unit of charge. We multiply that by the charge and we get the force. So that's a force at this position. Now we can go through the same argument we did in the preceding couple of videos, the one that preceded the last. And we're going to see that if we have a short interval or increment delta x of the x-axis, and I've positioned the x-axis so that it goes straight down here. We can position it any way we want. I left x as the variable so that what we're doing here looks a lot like what we did in the first video of this series, again, the video preceding the last. So the setup is very much analogous to what it was before. So we want to calculate the expression for the work done on this increment delta x. Well, that's going to be then the force times delta x. It's going to be 4 pi k lambda over x star multiplied by q. And the contribution to the work is going to be that times delta x. And that's going to lead us to the integral from infinity to r, from way out there to this position, of what? The force 2 pi k lambda times q over x times dx. So we integrate with respect to x. Everything else is a constant. The 2 pi lambda q comes out of the integral. The integral of 1 over x dx, antiderivative is going to be natural log of x. Natural log of x. Got a problem here. Back up. Okay, did something really ignorant, and I did this in class, so we got to modify this. If you do this total work, if you use infinity for the limit, well, you can't take the natural log of infinity, but we do know that the natural log increases without bound, and the natural log of infinity would then be essentially infinite. Now, more formally, we do this improper integral by letting this limit be c and taking the limit as c goes to infinity. Well, we get 2 pi lambda q times the limit as c goes to infinity. Not sure how legible that's going to be, of natural log of r minus a natural log of c. And natural log of c as c approaches infinity, so that this limit would be negative infinity. So that this work is not defined. It can't happen. And then the work per unit charge, which I originally had said hadn't bothered evaluating the integral at infinity, even though I know better, I wasn't thinking about that. If the work had been this times natural log of r, then the work per unit charge would have been the same expression except dividing out the q. However, it's not just natural log of r. The integral is actually undefined. It approaches negative infinity. So this should be negative infinity. You can't equal negative infinity, but the work approaches negative infinity. Now, what's that tell us? It tells us we can't get here from there. Okay? Can't get here from there. If you can't read that, can't get here from there. And that's simply because it would take infinite work to get anywhere from there, where there is an infinite separation. Now, of course, you can't be there anyway because you can't get to an infinite separation. But in this case, as the separation approaches infinity, the amount of work approaches infinity. So I make a further statement that the work approaches negative infinity as the separation approaches negative infinity, and that's the work done by the field. The work I would have to do would approach infinity as the separation approaches infinity. In other words, there's no limit to how much work I've got to do if I move further and further and further away and try to approach within distance r. Unlike the situation if I'm approaching a point charge, which is finite. Now, the reason is that the field of a point charge is inverse square with distance. The field of a line charge is just inverse first power. So let's talk in another video about why that is, just in case you missed it the last time. But the point here now is the work is going to approach, well, we can't talk about the work required to move from an infinite distance to a finite distance relative to an infinite line charge.